Hello, everyone. Welcome back to CP 517-WS Digital and Computer System Architecture. This is lecture 4, fast-stage pipeline. And here we're going to talk about hazards caused by structure, data, and control. Okay. So remember, we talk about we have 5-stage pipeline. The beauty of 5-stage pipeline is you don't have to do anything. We just have to let every function unit to be used by a different, each function unit being used by a different instruction so that we can have better performance, right? Then your question might be, what if this instruction, the instruction 2, is depending on the output of instruction 1 to execute? It seems like you need to wait until instruction 1 to be finished in order to dispatch instruction 2, right? So those are what we call dependencies or hazards. Taking them together, it means pipelining is not quite that easy. It's not so straightforward, which introduces a lot of research over there. The limits to pipeline are hazards, which prevent next instruction from being executed during its designated clock cycle. The hazards can be a structure hazard. That means the hardware component cannot support the combination of instructions. For instance, we typically say instruction fetch has to go to memory and memory access also has to go to memory. These two components might have some contention if we only have a single port of the memory. Data hazards are the most I would say the most popular one. Instruction depends on the output of the prior instruction. So we have to wait until the prior instruction to be finished and get a result to us, right? Control hazards is also very, very popular. It is caused by the delay between the fetch of instruction and decision about the change in control logic. For instance, we always assume using the PC as an address to access the instruction, but actually a lot of times, maybe we use a branch instruction, the PC might change. Right? So assuming the first structure hazard is what I just mentioned. If you have instruction, the first instruction is doing memory access, and the third instruction is doing instruction fetch, because both of them have to go through the memory port, then they might have contention. So we see this is called structure hazard. When structure hazard happens, what we're going to do is we're going to insert a bubble, right? For instance, a possible bubble is like we delay, we don't do nothing, okay? When it goes to instruction fetch, we just say, oh, the memory port is busy, so we delay for one cycle, right? That's the way we do bubbles. It's like some empty stuff is executing over there. So the speeding up for pipelining, if you remember our first exercise here, we assume we have pipelining, and then we have 3.7 times speed up because our CPI is 1. But actually, the pipeline CPI is not the ideal CPI. The ideal CPI is 1, but you have to include the average stall time per instruction, right? Then the speed up becomes the ideal CPI multiplied on the pipeline depth divided by ideal CPI plus the pipeline stall CPI. And then the cycle time, what we mentioned about previously, is 0.2 nanosecond, and then because we have some pipelining manipulations, so it makes the cycle time slightly longer, right? So if we do a little bit of canceling out, we figured out that the speed up becomes, if we divide ideal CPI from the both numerator and denominator, we figure out we have pipeline depth divided by 1 plus pipeline stall CPI. Multiply because ideal CPI is 1, right? So it's 1. sorry, it's not the dividing ideal CPI across numerator and denominator. It's because CPI is 1, ideal CPI is 1. So that's why we introduce 1 to replace ideal CPI. We got this pipeline depth divided by 1 plus pipeline stall CPI. Would you guys use whatever we learned before, use this speed up equation to do the exercise about here? Like we have a machine A, dual ported memory of Harvard architecture, machine B, single ported memory. But its pipeline implementation has a 1.05 times faster clock rate. Ideal CPI is 1 for both. Loads are 40% of the instruction executed. Load will conflict with the instruction fetch. Which machine is faster? Using 15 minutes to deal with it, okay? Can you pause it for 15 minutes? Okay, welcome back. So here we have this speed up of A over the non-pipelined case is the pipeline depth divided by 1 plus 0 because you have dual port. So you have no stall here. Right? And then multiply the clock unpipelined and divided by clock time of pipelined. So the speed up is pipeline depth, and then speed up for machine B is the pipeline depth divided by 1 plus the pipeline stall is 40% by 1 cycle, right? But you're gonna have a 1.05 times faster cycle time, right? So it's 0.75 multiplied pipeline depth. Then we see the speed up of A over speed up of B is 1.33 times. So we see because you have the dual ported memory, the Harvard architecture is actually 1.33 times faster. Okay. Okay. Right, the speed up is over the unpipelined case. Right. All right. So we finished the structure hazard and okay, this is sorry, it's only structure hazard finished. And then we go to data hazard. So for data hazard, we have this kind of stream of instructions: add R2 and R3, put the results back to R1, and then subtract R1, R3, and put it to R4, and R1, R7, put in R6, or R1, R9, put in R8, XOR R1, R11, and put in R10. So we see here, the output of R1 is actually required by second instruction, third, fourth, and fifth, right? So there's dependency here. Clearly, when we're trying to fetch the value from the register file, because it's not yet updated by the write back, then this value would be stale. So we basically have to wait until the first instruction to be finished. There are 3 generic data hazards. First is read after write. That's what we mentioned here. Read after write. Okay, this is a true dependency. Sorry, there's a typo here. So there's actually a space, not a typo. So instruction J tries to read operand or value before instruction I writes it, right? This is caused by a dependency in compiler. This hazard results from an actual need for communication. We really have to do that, basically. This is not that are wrong in dependency, right? Okay. Write after read. Write R1 after you read R1. This would not be like data hazards if we do single threaded execution, like we execute instruction I first, finish instruction I, and then execute instruction J and finish instruction J. If we do this in order, in single threaded, we will not have this kind of problem. But if we do multi-threaded, like instruction I would be finished early or late, then later the instruction J, or we'll do out of order execution, which we're going to discuss in a couple of slides, a couple of lectures. Then it's likely instruction J might finish earlier. Okay. So for this kind of dependency, it's like an anti-dependency. It's like not dependency, right? We can intuitively feel remember this like that way. For anti-dependency, this results from the reuse of the name of R1. This will not happen in MIPS 5-stage pipeline because all instructions takes 5 stages and reads are always in stage 2 and writes are always in stage 5. And assuming the instructions are in order, right? Write after write or while. Instruction J writes to R1, instruction I also writes to R1. This is very similar to what we discussed in anti-dependency. It's called output dependency by compiler writers. This also results from the reuse of the R1, but it typically cannot happen in MIPS 5 stage because all instructions take 5 stages and the first writes definitely happens earlier than the second writes if we do them in order. However, what we mentioned before, or while, like write after read and write after write would happen if we if it is very complicated pipelines. For example, like the out of order execution or speculative execution, which we're going to talk about later, or even multi-threaded execution. Okay, so taking all of them together, I think the data hazards, we can think it as raw, or while, right? So there's 3 of them. The first one is the true dependency. Second, third are anti-dependency and output dependency. Especially the second and third, they can be easily addressed by register renaming, okay? I think we're gonna talk about that later. So for example, we use R5 here, then there will never be a dependency anymore, right? Okay, similarly for the anti-dependency. Anyway, so that's it for this part.